Good morning, everyone. So today I'm going to present about an improved method of constant time discrete Gaussian sampling. I'm going to present this in DAC next week. This work is actually improvement on our previous work on constant time discrete Gaussian sampling, which appeared in Transactions in Computers in November 2018 issue. Okay, well, so a little bit introduction. So you know, our most current public infrastructure is based on RSA and elliptic curve discrete logarithm problem, but this is going to be useless once these quantum computers arrive. So we are working on post-quantum cryptography to nullify the threat of quantum computers. Yeah, so consider these two sets of linear equations. This is like exact linear equations, and this is on approximate linear equations. So if these are our known values, it's very easy to get the secret values using Gaussian elimination. But here it doesn't work because these errors are added. That's make it approximate linear equations. So if we try to do Gaussian elimination, in each pivoting step, this error actually blows up and it cannot be solved. And it turns out that it is actually a quantum hard problem. It cannot be even solved even using large quantum computers. And this is known as LWE. This is a very popular problem to construct post-quantum public key cryptography. This one are some variants of this, like the rings or modules. Well, so how these errors come from? Traditionally, this used to be sampled from the discrete Gaussian distributions. Now, in many applications, these are actually this discrete Gaussian distribution has been replaced with uniform distribution or binomial distribution, but still some applications use them mainly because the proof of security are better, and in case of signatures, these are actually if you use Gaussian distribution, the size of a signature becomes very small. So these Frodo is actually a key encapsulation mechanism, and this is a Falcon. These are both entry into this NIST's ongoing post-quantum standardization procedure, and they both use discrete Gaussian distribution still. Well, so how do you generate this? So a very popular method to generate a sample from discrete Gaussian distributions are like Knuth-Yao sampling. So for this, we first create a DDG tree. It's called the discrete distribution generation tree, and it's actually a binary tree. And here these are like the root node. These are intermediate nodes, and all the samples in the sample space are actually kept in the leaf nodes of this DDG tree. But how these are placed, this actually depends on how, I mean, the probabilities of this value of these each samples in the distribution. So to generate a sample of, we actually do a random walk from root to node, root to leaf for in the DDG tree. Let's see how we do this. So at starting from the root, at each step, we generate a Boolean binary variable, and depending on the binary variable, we either take the top sub branch or the bottom sub branch. So let's start from root. Our first random bit is 1, so we took the bottom sub branch. Again, we generate a random bit. This time it's 0, so we take the top one, but we still haven't hit the leaf node, so we'll go on. The next time we get a binary bit 1, so we take the bottom one, and now we have hit a leaf node. So now we return this 2 as a sample and terminate the procedure. But let's consider these two random walks marked in green and blue. I mean, you can clearly see that the number of steps to generate these two samples are different. So I mean, it leads to a non-constant time sampler. And it turns out that almost all the discrete Gaussian samplers which are used today actually runs in non-constant time. This is mainly because of the efficiency. And attackers can use this information to like extract lots of information about these noises and errors and the secrets. There exists actually very efficient side channel attacks which can exploit this information to like completely break the crypto systems. For example, the Bliss signature scheme. So there, of course, there are some simple countermeasures, but most of them are have very poor performance. There are some which cannot be proven secure in the side channel security. Actually, this problem was open problem for a long time. But okay, so in our previous work we first noticed that, okay, let's say this DD tree is a binary tree, right? So there exists an unique path from root to each leaf nodes. This means that each of these samples are generated by a unique random bit string. Well, this means that there exists, and because these samples, multiple samples can one sample can occur in multiple leaves, there exists a many-to-one mapping between the set of input random bit string to the sample values. For example, here, I mean, so we can express each bit in the output samples as a Boolean function of this input random bit string. For example, here, let's consider the most significant bit of the samples, S1. So you see, S1 becomes 1 only when the sample is 3 or 2. And 3 or 2 happens only when the input random bit string are of this format. We can express this S1 as this Boolean function. Well, if I say more generically, so if our samples can have maximum m bits, I can express each sample by m Boolean expressions. I mean, if the depth of the tree is n, then each expression has I mean n binary variables. So and notice that each of these if I execute each of these Boolean functions, because these are same and it doesn't depend on the values of these random bits from one execution to another execution. So I can generate m bits of a sample all the time by executing these Boolean functions one by one. And as all of them are takes, I mean, it is input independent. It takes constant time for each execution. That's how I get a constant time sampler from discrete Gaussian distribution. Well, so yeah, this is our previous work. I mean, so you can understand that the efficiency depends how well I can execute this, how fast I can execute these Boolean expressions. And of course, so that's why we have to do a very good minimization on this on each of these Boolean expressions. So yeah, this is a small example. So here I have an Boolean function which is like unminimized, and here I have one minimized which is not so well minimized, and this is a very well minimized Boolean expression, and these all three are equivalent. They all calculate the same function. But I mean, you can see there are much more operations than this, so it will take a longer time to execute than this one. So if I so the efficiency of the whole Gaussian sampler improves if I can minimize all of my Boolean functions very well. Well, but this is an NP-complete problem. We know this. So there are some methods like Karnovich map or Queen-McCluskey method, which for small values, for let's say if n is equal to up to 16, this works pretty well. This is kind of brute force method, but it doesn't scale. In our case, n is more than hundreds most of the time. Well, but this problem is also equivalent to the circuit minimization problem, and it has been studied for a long time. And I mean, to reduce the power consumption or area of the, I mean, in circuit boards, there are some commercially available tools like Synopsys, Cadence, which can do this minimizing procedure. But there is a problem. Okay, so let's see first. Let's see how they do this. So we have our this long list, like our random bit and then their corresponding samples. We put them in a file, and then we put we give them as input to some synthesis tools, and they actually generate some values in their internal representation. But from there, we can write our own custom parser that can actually read these internal files of these softwares, and then can generate or minimize expressions. But the problem is, these tools actually uses lots of heuristics. So how well this Boolean functions will be minimized, that's very unpredictable. We cannot control the internal working of these tools. So it may happen for some standard deviations, these are very efficient, for others it's not so much. But the biggest problem is these algorithms, how do they minimize these expressions, are all protected by intellectual property law. So I cannot put these values outside, I mean I cannot put it in the public domain. So that's actually, I mean it's not suitable for most of the cases. And yeah, I mean sometimes it can even destroy this constant time property, it can put some if else in the between, and I mean we cannot control that, I mean we don't know. So yeah, we cannot use this. Okay, so so that's why we created a very let's come to the next slide. So first we saw this property of this discrete Gaussian, the property of the DDG tree for the discrete Gaussian distributions. We noticed that for discrete Gaussian distributions, the DDG tree is very skewed. That means that the input random bits that actually hits the leaves have this particular property. That means they have a like trailing 1, then a 0, and then some binary, then some variable binary bits, and then some don't care options. The important thing is that this variable binary bits has to be very small. The j is very small. I mean usually less than 5 in most of the cases. Otherwise this tree is not skewed. So yeah, this is, so using this theorem I can show that I can devise a very well divide and conquer strategy to minimize my Boolean expressions. Well, so my first stage. So first I got this this random bits and their corresponding sample bits, right? Now I sort them in the ascending order of trailing ones. So here you see in this one there is no trailing one, there is 0, and this is 1, this is 2, and so on. In the next stage I split them such that I split them smaller lists L0 to LL, such that the ith sublist has only I trailing ones. Okay, this is, I can split them in the sublist. In the next stage, now consider this. This is one of my sublist. Now due to my sorting, this first k and the 1 bits are constant. It doesn't change. So the output only depends on this binary variables, which varies mixture of 0 and 1. And remember from theorem 1 I said this j is actually very small. So now it's perfectly feasible to do a brute force method to minimize these expressions because these are very small. So for each sublist I use any brute force method like KV map or MC method to generate smaller Boolean expressions for each list. But it's not our complete the whole minimized expressions. We have to somehow combine them. So to combine them, let's first so at this moment we have this many smaller sub expressions. We are going to combine them. So let's consider this variable c, okay, and this has this particular structure. Now I claim that the c becomes 1 if and only if the input random bit string belongs to the list Li. I mean it's very easy to verify because consider C2. So C2 is this. So when I do R0 and R1, so this becomes 0. So it doesn't matter what lies beyond this. This will always be 0. For C2 is of course 1 because it belongs to L2. For L3, because there are 3 trailing ones. So when I do R0 and R1, it's fine. This is 1, but when I do not R2, this actually becomes 0. And again, it doesn't matter what it's beyond this, because it will stay at 0. So it is true for all all sublists which are greater than 3. Okay. Now actually we can combine this all of them all of these sub expressions using a long chain of if else if constructions. Well, I mean, using this C value of C as a condition. So like the C is actually acts as a multiplexer. So when it gets some random bit strings which belongs to a particular list, it actually outputs that the minimized sub-expressions from that particular list. But I mean, I have put an if-else if here, so it destroys the constant time property. But actually, it's very easy to do if-else using a constant time, and this is known from like the bitSlice implementation of DES, like on for very long time. So yeah, and this can be extended up to like arbitrary length of if-else if I mean up to arbitrary depth of this if-else if chain. So this is how we actually combine all of this to all of these smaller sub-expressions to a Boolean function, which are of course very minimized and mimics the whole table. Well, okay. So for results, so right now it is the fastest known constant time discrete Gaussian sampler. And yeah, another output of this work is that we provided a like tool which can automate all of this process. So you can just put your n and your standard deviation, it will do all of these things and output a standard constant time discrete Gaussian sampler. We did a case study with this Falcon signatures. We replaced their non-constant time sampler with our constant time sampler. Well, it's 15% faster than the best known constant time sampler, but it's 32% slower when compared to the non-constant time sampler. The reason is that, well, executing these Boolean expressions are easy and they are very fast, but the generating random numbers are really hard. I mean, even if I use PRNG. So I mean, I benchmark this and almost 85% of the time is taken just to generate the random numbers alone. So this is the biggest bottleneck. That's fine. Okay, so yeah, this concludes my talk and I would be happy to take your questions.